So our work today is Starfish, efficient concurrency support for computer vision applications. And this is part of a line of work we have towards our vision of vision, in which we make a bet that 5 years from now, in the year 2020, we'll have continuous mobile vision devices. These are always-on wearable devices that could do tasks, different apps, like a social logger, remembering who we've talked to, or maybe more importantly, who we haven't talked to. So then I could say, hey Fred, we haven't talked very recently, do you want to catch up for an espresso maybe? Or I could have an app to remember, where are my keys, where's my passport? So if I'm in a rush trying to get to MobiSys, you could say, hey, your keys are over there, your passport's over there, go pick them up and get out the door. Or it could have an if Lin then that application, where Lin's my advisor, and it would be always looking out for Lin, so it could remember to tell him, I could remind myself to tell him something really important the next time I see him. Or many different kinds of applications. I mean, we've got kind of applications in medical informatics, food logging, visible light communication, as we've seen today, social media, and we optimistically assume we could probably support any one of these. Looking at the track of kind of research we've been doing and others in the community have been doing, we'll be able to support at least one of these. But there's a fundamental problem when we want to support all of these, because we want the full gamut of all these applications on at the same time, running in the background so that it could alert us or it could remember things for us, right? We don't want to have to manually turn different things on and off. The whole point is to remove the burden on the human, right? But the problem is that we'll have low battery. The energy consumption of running all of these at the same time is going to overwhelm that wearable battery, that really small battery. Because there's insufficient support for computer vision. Now, to see why that is, we can look at how things are typically done today. So typically, a camera service, the capture service, generates frames and sends it to the application, where the application can do some processing on that. But because the developer doesn't want to have to play around with the algorithms themselves, do the implementation hacks, they're going to use vision headers and call into a typical vision library. For example, OpenCV or FastCV, maybe in the future, OpenVX. And this vision library will do the work for them. It'll generate some primitives out of this root frame. It'll generate like scaled down representations of the image, or find the face inside of the image, or many other things. You can check out the OpenCV API wide with different kinds of functionalities. But if we try to extend this to multiple applications, because there's no concurrency support, you have to capture a different frame for each of these applications. You have to compute again for each of these applications. So the camera is overworked, the computation is overworked, because we're time sharing the capture, we're time sharing the computation. And so it's right now impossible to run multiple vision applications with low energy and high performance. That is, we desperately need efficient concurrency support. So how do we get there? How do we as a community look at these problems? Well, we typically take observations, right? And we look, vision applications usually use a common vision library. Like I've been saying, there's OpenCV, for example. It's a very typical library lots of developers will want to use, especially if there's system support for concurrency on them. And at the same time, the capture and the computation generated through this library is very redundant. These primitives that frame itself, useful on all those applications. A scaled down representation, also useful, very useful across a wide number of these things. Or the face, right? Many different applications will want to use the face. All these social media things will want to use a face. All these different entities, right, running on the background on this device. So anyway, lots of redundancy, and we could look at that as a bad thing, or we could leverage that to introduce benefit into the system. We decide to do the latter, and we design a split process design for centralized control, sharing computations to reduce the redundancy in the system. This is kind of an abstract way of how it looks, but how do we actually do this? Well, we look at these applications again, and we look at the way they typically do things, right? They use their vision headers, right, into those vision libraries. We don't want to change, we don't want to be an extra burden on those developers, so we allow them to keep using those vision headers, that original vision library. But instead of hooking into the vision library, we use our custom Starfish library solution to intercept any library calls. And we send those to our Starfish core service, which then can execute, track, and share library call computations. Together, this split process, you see you've got processes over there, a central process over here, it creates a split process library solution for efficient, transparent, multi-app service. That's Starfish. It's called Starfish because it looked like a starfish when I drew it on Lin's board when I proposed it to him. But how does it actually do this tracking? How does it do this sharing? Well, it's pretty simple. It's basically what you'd probably expect even. You've got the Starfish library on one side. It wants to do a face detect call. This first application wants to do a face detect call. So it sends that face detect function pointer, it sends the image over to the core service, and it checks, have I seen this before? And if it hasn't, which it hasn't because it's a first call, it'll have to do this library execution, and then it'll store the result in that function cache for later use. Of course, it returns the result back to the library right there, and it goes happily on its way with that if then that application. Now this social logger wants to do the same thing, right? It's also doing a face detect, an image. So it too sends the function pointer for face detect. It too sends the image over. And now the Starfish core is like, hey, I've seen this before. I don't have to do this work again. I can just send you right to the function cache, retrieve the results out, and send it back to you. And that's really great because now, even though the first call had this execution overhead of 20 to 200 milliseconds of doing this vision library execution, the subsequent call can skip that execution, right? At 0 milliseconds because you're skipping it entirely when you're retrieving the results. So Starfish is able to use this to share computations and reduce redundancy across a great number of applications. Now we do some timing optimizations. We reuse recent frames to promote the amount of cache hits. We want to increase the sharing, encourage the sharing, like kindergarten, right? And we also delay the call return to encourage the device to sleep and to maintain developer transparency. I'm intentionally going to gloss over these points right now because I think there's a much more important problem that we want to look through, and that's actually mitigating the split process overhead. Inherent to splitting any process into two is that you've got this overhead of running two applications, but more importantly is sending arguments between the two, argument passing. It's a classic problem of doing this IPC. So sending that frame across, it's a lot of data. Getting the face back, it's a little bit of data, but it's still substantial. But if you're doing this among all these applications at once, it's going to be pretty burdensome because you're doing a lot of traffic there. And we really want to reduce the expense of that argument passing then, this IPC. At the same time, we want to avoid modifying those library objects. What I mean by that is like OpenCV defines a mat structure where you've got rows, columns as integers, you've got a void star that points to the data, right? You've got flags for colors like that. You don't want to mess with that because otherwise the applications won't know how to deal with this frame later, and they won't know how to generate the input data either. So you kind of want to step away from that. So we don't want to modify these library objects. So it's challenging, so what we did, like we always do, is we looked to the literature for inspiration. And we found good inspiration here. There's two classes of things we saw. Was object redefinition, like lightweight RPC, Sun RPC, where they redesigned the library around this concept of we're going to be sharing these objects later. So they encourage a very zero copy kind of design because they're able to just transmit their shared pointers. At the same time, we look at cloud transfer, code offload kind of works, like Comet, Maui, Clone Cloud. And while these are optimized for code offload, they usually use an object tracking. So they maintain, because network is really expensive, right? So they want to know, have I sent this object before? Does the cloud have a copy of this object already? Or do I have to transmit a new copy over there? Now again, this is optimized for code offload, so it's more about trying to minimize the network rather than trying to minimize the split process nature. But we looked at both camps and we tried to apply it to our design. So taking a step back, let's look at how it's typically done with Android services, etc., iOS services, etc. And usually you've got one application on one side, in this case the Starfish library, and you've got the service on the other side, which this is the Starfish core. You've got your data over here, You've got your data on the left side, and you've got your core on the right side where you want to do the execution. So how do you get to there from here? Well, you usually use a shared memory buffer. This shared memory is accessible from both applications. And you copy your arguments in. So you allocate a region in shared memory, you copy all your pixels into that shared memory, you copy all your pixels out of that shared memory, you execute on it with the vision library, and generate that face. Now you allocate some more memory in that shared memory so that you can put the face in there and send it back to the Starfish library, where it can go happily on its way and use that face. It's detected that there's Lin there. The problem is that this deep copy is really expensive. It's 3.5 milliseconds on a Google Glass to do a 640 by 360 color frame. So if we're doing this multiple times, right, here we've got 4 different instances of deep copy. It's pretty expensive for each call, right? So our goal is to then minimize that deep copy. We use a few techniques to do this. We use a protected shallow copy. So shallow copy means instead of copying all the pixels out, you just point to the object is over there, so just access it over there. But we also don't want to modify the objects inside the shared memory, or it will impact our cache. Our cache needs to know all the input and output arguments, otherwise it won't work for the next guy that comes along. Right? So we mark this with a copy on write by doing an mprotect, a memory protect on these received objects. The next thing we do is to eliminate this red arrow over here on the bottom right. We're copying that output into the shared memory buffer. Wouldn't it be great if we could just write the new data directly into the shared memory? So that's what we do. We just we intercept any calls into malloc, and instead of giving it a new memory buffer, we actually just give it the shared memory. And so it will write the objects directly into there, saves a copy on our part. And then the third thing we do is to reduce that last red arrow, is to reduce the input arguments. And this concept, reusing arguments from prior calls, is basically around if the Starfish library, if the Starfish core has already seen the object, we really shouldn't have to send it again. I mean, this is the thing that we got from the code offload works, right? So we should just track these objects, and any input or output objects into Starfish we'll track, and we'll say, okay, we don't need to we don't need to copy all those pixels into the buffer. They are already there. Now, this may seem like it's not very useful, but it is actually very useful, because in Vision you usually have streams of processing. You have capture, then you do scale, then face detect, then face recognizer, one after the other. So the output of one function is usually the input for the next function anyway. So the Starfish library is going to be creating most of this data through that direct execution directly into the shared memory. This makes it a usually zero copy argument passing throughout the entire system. Usually because, again, you may not have seen that input argument before. You may be modifying these objects. But typically, for most of the cases we've seen in Vision library execution, it does reduce the number of deep copies through argument reuse, typically down to 0. We also reduce allocation through buffer reuse, and I'm skipping that again because for interest of time. But that rounds out our Starfish optimizations, where we're able to share computations and decrease redundancy to provide efficient concurrency support through the system. So right now, up till now, I've described the very abstract terms of our design. How does this actually work? So we took a Google Glass, which is running Android, and OpenCV, and we chopped off its battery for surgery on the Google Glass. And we hooked it up to a Monsoon power monitor instead, so that we could see how much power is this Google Glass consuming when doing Vision applications without Starfish, with Starfish, and with Starfish with the memory optimizations that we've just discussed. And so we put Starfish on there, and we ran some benchmark tests. There's a lot of tests in the paper, but I'm going to focus on some key results we found right now. So breaking down a library call, right, and seeing what the overhead is here. Well, for a resize call where we're trying to resize a frame from a bigger one to a small one, we're looking at this, the native execution time is 21 milliseconds, so can we reduce that by using Starfish? Well, if we use Starfish without optimization, it consumes actually substantially more overhead, 42 milliseconds, because we're doing that argument passing this deep copying. But if we use Starfish with the optimizations, so after, we can slash that in half, down to 24 milliseconds. These memory optimizations cut Starfish overhead in half. That's for the first call, but for the second call, we have a much smaller overhead because we don't have to do that execution the second time around, right? We're skipping that. We cache the results so we can take advantage of, reap the benefits of this labor, is just skip that execution. Again, we can slash the overhead in half, but I think the more important thing that this graph will show now, and these numbers together will show that Starfish actually works well when we have these memory optimizations, when the native function execution is larger than that per call overhead of 5 milliseconds. So it works really well, again, when that native function execution is more than 5 milliseconds, but the corollary is true, unfortunately. That is, this 5 to 6 millisecond performance overhead means that it's going to be bad for fast computations. Anything that has very low latency on the Vision library execution, for example, like color transforms, like grayscale. You're just throwing away the U and the V in your YUV. So that's a cheap execution, and Starfish won't be able to improve that. Starfish will be bad with large, deep arguments. So like if you've got a really deep linked list, and so you have to do all this manage all those pointers, not so good for Starfish. So you'll have to avoid those as well. Non-cacheable functions, those with random dependencies, for example, we don't want to cache randomness because then it's not very random. And as well as file system dependencies between different processes, they have a different concept of the file system, right? So it doesn't work so well with some things, but with these high-level functions of face detect, corner detect, image resize. It's very useful. And so how useful is it? When we apply it to these multi-app workloads, right? We've got 1 application, 2 applications, 10 applications. I don't know what the future is going to be like. Everyone here is coming up with new ideas all the time, right? So maybe we have a plethora of these things running, and they're all trying to do this face recognition. And I argue that we'll want to do this fairly passively, so like one frame every 3 seconds, for example, and they're all going to be doing this scaling, face detection, and face recognition. So how well does this work? Well, as we expect, Starfish will incur an overhead over the native if we're just running 1 app. Because we're doing this split process, we're running 2 processes now instead of 1, and we're doing these we see some great benefits, right? We're going to see a linear increase in workload because with every increase in app, we're going to see the vision workload increase. But with Starfish, we're able to mitigate that because we're able to share previously used computations. And so Starfish, by sharing these computations and reducing redundancy, is able to achieve efficient concurrency support. Now, this is one step towards our vision, right? Our vision of vision, our continuing mobile vision of continuous mobile vision. There's still a lot more work to be done. This is a big mountain, lots of challenging foothills, mitigating analog signal chain. Analog signal chain is a big power consumption unit in the chain. We need to figure out ways to reduce that. We need to preserve user-subject privacy. We can't be violating everybody's privacy while we're going on with these devices that are always looking out, right? We want this to be always on, but we want it to be private also. So we have some ideas along that dimension too. And of course, right, it goes without saying, designing efficient systems. Whether this is using cloudlets, whether this is using GPU, we're not purists. We'll do anything it takes to design an efficient system to get this done, to make this vision of all these applications running smoothly all at the same time. So together, join us, collaborate with us, hire me, so that we can achieve our vision of continuous mobile vision. And Starfish is one step towards that direction. Thank you.